It'll be the most computational week we'll probably ever have. So if you do this in like a class like Math135 or something, so what are we going to talk about? We're going to talk about integration techniques. And we can just like even declare that. Integration techniques. Okay, so obviously this used to be much more relevant when, we didn't have computers that could just solve everything for you. But, as times move on and we have computers, not as important anymore. That being said, theoretically, there are still a couple of tools that we need that are super useful. But, we're not going to spend like 2 weeks doing a whole ton of integration techniques because it's just not useful. There are a lot. So for example, we'll talk about substitution and integration by parts. And if you're familiar with those things, great, but we're not going beyond that. So for example, there's trigonometric integration, trigonometric substitution, inverse substitution, Barstow substitution, rationalization, partial fractions. What else is there? And then, differentiation under the integral sign. And then like lots of really obscure stuff, right? So we're, for the most part, not going to worry about most of those. We just don't care. We're going to focus on the big two. So the big two are substitution and integration. Yeah, sure. And numerical integration is like its own thing. It's quite different, right? Like it turns out, because your first order approximation would be to do something like actually use a Darboux sum or an upper lower sum or Riemann sum in order to approximate the integral. Turns out that's not the best way of doing things. Pretty much one of the best ways that you can do things is Gaussian quadrature. So if any of you are interested, go check it out. The mathematics is not terribly difficult, but it still looks like magic to me. The fact that, Gauss figured out this way of evaluating integrals basically just by evaluating the function at a couple of important points and then weighting it is just madness to me. So that's a really, really cool thing. Okay, so but we're not going to do that. So we'll talk about substitution first, and we should get to parts today. We'll see. Okay, so we're going to start with substitution. Sometimes it's called U substitution. I don't like that. I think that's stupid. So, okay, what's the idea? So the idea, so we learned from the fundamental theorem of calculus that integration is morally the inverse of differentiation, which means maybe we can use some of those rules that we learned for differentiation in reverse in order to help us integrate. So the first thing is going to be substitution, and that's going to be the chain rule in reverse, right? So suppose that capital F is an antiderivative of little f, right? So remember, by that we mean f prime is equal to little f, like that, okay? And g is just some other function. Let's say C1, right? Just we really only need differentiable, but you'll see why we need C1 later. Okay, so the chain rule, which we're all very well aware of by now, so that if we want to differentiate f of g of x, that gives us this, g prime of x, and then capital F prime is little f, like that. Okay, and all this says is the following result, which you're going to be like, this is dumb. Why did we even state it? But you'll see in a second. So proposition, if little f is continuous with antiderivative big F and g is C1, then f composed g is an antiderivative of f composed g prime, right? And the proof is just literally what we did above. It's the chain rule. Okay, so how do we use this? So the way that we actually use this, though, because we haven't really done anything, we were like, oh yeah, okay, it seems like you just wrote down some sort of complicated chain rule thing. The way that we're actually going to use this is the following. So that is the indefinite integral of this thing is f of g of x plus c, and the integral from a to b, so the definite integral, right? Well, that's going to be f of g of b minus f of g of a, right? Because this is what the FTC tells us, that these two things are true. And let me just actually rewrite the second one in a slightly different way, because you'll see why it's called U substitution if we do this. Right? So I've rewritten this, capital F evaluated to g of b minus capital F evaluated to g of a as this integral on the right-hand side. And really, this line tells us what we're trying to do, okay? So it says what we're trying to do is we've got this integral on the left-hand side, right? We've got this thing right here. And what we want to do is somehow transform it into the integral on the right side. Because if we can transform it into the integral on the right-hand side, and then we can find an antiderivative for little f, then we can evaluate it much, much easier. Okay, so at the end of the day, all of this thing looks, again, looks silly. It might not be obvious how we use this. So let me give you just kind of a quick strategy. And then once we do a couple of examples, you're like, oh yes, okay, I see how this is done. So one, identify G. So throughout all this, you're never going to have an idea of what F is. Okay, you'll only know what F is when you're done. When you start, right, you're starting with this thing right here. You have no idea what the functions F and G are. You need to choose them. So what we're going to do is we're going to try and identify G by looking for G prime, right? So both G and G prime appear in this formula. So we're going to look for something and its derivative. And if we find that, that's a good suggestion that we should use that as our G. Then what we're going to do, and this is why it's called U substitution, because we often use the same variable. What we're going to do is we're going to create a new dependent variable U, and we're going to call that G of X. Okay. Now, the next step is critical, but is somewhat blasphemous. Like, you totally are not allowed to do this in general. So set U to be G of X. So that du is G prime of X dx. Okay. This part is critical. What we're effectively doing, even though I've said a million times, you can't treat this thing like a fraction. This is what we're doing here. And there is, again, a sense in which this formally makes sense. Like, if you know what a differential form is, this is okay to write down, but I'm not going to tell you what differential forms are because that's way too hard. So what I want you to do from now is think about this. Like, if I were to write du dx, that would be G prime of X. And then I'm now going to pretend that dx is a fraction, du dx is a fraction, multiply both sides by dx, and that will give me this du is G prime of X dx. Okay, and then what we're going to do is we're going to substitute that into our integral. Sub into the integral. Okay, so when we do that, right, so I'm just rewriting the original integral here, G prime of X dx. Okay, this thing here, right, that's U. And then this whole thing here now, that's du. And so now when I make this change, right, when I make the substitution, and, don't forget to change your bounds here. We said we had to change the bounds in order to make everything work out. That gives us f of u du. And now our life is much easier to solve. Okay. And then I'll point out that there's a lot of blasphemy going on here. We'll do that in a second. Let's solve an example first, because right now I've just kind of been talking about how it works in general. So I think, we should try and actually solve something. So just so you can kind of get an idea of what it looks like. Out of curiosity, who has seen substitution before? I suspect a good number of you. Yes, I'm cursing at you all. Okay, so a couple of you have. It's always so tricky, right? Because some people have done integration when they learn. People haven't, right? Some people didn't do integration at all. If they did, they did see it. I suspect though anyone who saw integration probably saw this, right? So let's say we wanted to do this thing. You can imagine this is a little bit nasty. Like this isn't the sort of thing that you're probably going to be able to easily find an antiderivative of without doing some sort of manipulation. So this is our goal. We want to do some sort of manipulation here. And if we look at our strategy, right? So think about what we're trying to do. The first thing we want to do is trying to identify g. So we're looking for a function and its derivative. And the thing to always keep in mind here is that when you're doing this, you generally don't care about multiplicative constants. Okay, multiplicative constants don't mean anything to you. So when I look at this equation, and for those of you who've done substitution before, I know you can probably see it immediately. Exactly, let u be 3x squared plus 7. Okay, and the reason for this, let's clarify why this is true for anyone who hasn't seen substitution before. The reason for this is this thing right here. You see this? Oh man, that does not look good. Yeah, we're going to use yellow. So the idea here is that we look at this, we see an x squared, right? And then we see its derivative, just x. And again, let's not worry about the constants, right? Because we know differentiation and integration are linear, so we can always take those scalars out and kind of like manipulate things in order to make sense. Just look for a rough, roughly the right things. So we've got here, an x squared and an x. Great, that those two things seem to be related. That's an idea that we should use those as our substitution. Now, when you set your substitution variable, when you set u, you might say, well, why didn't we just do x squared? Well, put as much into that variable as possible, right? Because you're basically making things vanish. Anything you put into u is just going to vanish from your equation. So as a general rule, you should put as much into it as possible. So we're going to put the 3 into it. We're going to put the 7, because the 7, right, we know when you differentiate it, it doesn't give you anything. It's just a constant. Anytime you have an opportunity to throw constants into your substitution, you totally should do it. So we're just going to pack as much into that thing as possible. Okay. And when we do that, so u is this. Now du is 6x dx, right? Because we have to differentiate it and then we throw that dx in front. Now, again, we're not worried about the fact that there's a 6 in du, but there isn't a 6 in our integrand. We're not worried about that. There's a couple of ways you can fix this. I think kind of the traditional one that gets you in the least amount of trouble is just to kind of take this thing and just rewrite it, divide both sides by 6. Maybe let me write that as 1/6 du is x dx. Okay, so substituting. Oh, I guess, we should say what the bounds change to, right? While we're here. The bounds become, right? So the lower bound is -1. Yeah, exactly. Yeah. So that's sort of the other way, is that you could like say, oh, I've got that 2 there, so I'm going to keep a 2 and then just leave the 3. That definitely works. The reason I'm not a big fan of that is sometimes it doesn't work out that you actually can factor it out. Like let's say it was a 7 or something, like you're not going to, I mean, you could, but you would have to write it as like 7/2 times 2. It's not great. Yeah, exactly. But if you want to do it that way, you totally can. So the bounds, what we're going to do is we're going to plug x equals -1 in. What does that give me? That gives me 10. And if I plug 2 in, that gives me 4, 12, 19. So now our integral becomes, and let me write this really suggestively, okay? So first of all, I'm going to take that 2 out because I don't care about it. And I'm actually just going to rearrange the integrand. Okay, and I'm going to put the x over here beside the dx. You don't have to do this. Like once you get comfortable with this, by all means, just go straight to the answer. But the reason that I'm doing this is that I very specifically want to point out that this thing, this whole function here, this is going to become u to the 12. And then this thing here this is 1/6 du, right? So once we do all of that, don't forget to change your bounds of integration. We're going to u to the 12 times 1/6 du. And yeah, I'm going to pull out that 1/6 and just make it a third. Okay. And the thing that we're left with now is really easy to integrate, certainly much easier to integrate than our previous thing was, right? So we know how to integrate this. So we're going to get 1/39 u to the 13 from 10 to the 19. I'm not going to figure out what these numbers are because I don't care. 19 to 13 minus 10 to the 13 over 39, like so. Okay. And of course, you know, we could have just, if it wasn't a definite integral, we could have just stopped. In fact, we'll do, most of the examples that we do hereafter will actually be indefinite integrals, because of course, if you can find the antiderivative, then evaluating the definite integral is just plugging it in. Right? Okay, but are there any questions about that? Does that make sense? Everyone's happy? And hopefully you see here why I was like, don't worry about the constants, right? Constants will all just work out. They might be gross, but it doesn't matter. You're just going to pull them all out and just throw them all together and smush them up and be like, all right, hopefully, you know, I did things correct and I remember how to multiply fractions, but it all just comes down to multiplying fractions. Like, who cares? Right, okay. So this, I was wondering if I mentioned this at some point. This long bar here just means it's a placeholder for the evaluation. So it means I'm going to use the FTC and I'm going to plug in the top number and subtract the bottom number. So this means evaluate the difference of the top and the bottom numbers. The difference when the top and bottom are plugged in, right? So in particular, where this comes up is in the FTC, we often have f of b minus f of a. And so we'll often write this as a shorthand, right? This means f of b minus f of a. So that just gives you the ability, like when you're doing your calculations, if you don't want to go straight or like write your antiderivative on the side in order to be able to plug it in, it just gives you the ability to kind of like do it step by step without having to write some stuff on the side. All right, so it's just notation. Do we need to care about the variable when using the bar? Right, actually, yeah, this is a great question. No, right? So long as we specifically changed our bounds of integration so that we didn't care about the variable. So this is actually, this is a really great point. Let's maybe take a look at what happens if we wanted to change back to x's, right? So right now our variable is in u and we're evaluating u from 10 to 19, but the original integral was x as x went from -1 to 2. So at this point, right, what we could have done instead is turned, instead of 1/39 u to the 13, evaluated from 10 to 19, what we can do is we can return back to x's, okay? And we know what u is, right? U is 3x squared plus 7. So if we return to the x's, s of 13 over 39, when I evaluate, I also am going to go back to -1 and 2 now, right? So if you want to, you can go back. And then if you evaluate it, well, but you see, you get the exact same answers, right? You still get 19 to the 13 minus 10 to the 13 over 39. But this is a great point, especially because there are occasions where your bounds are actually really, really nasty. And you're like, okay, I don't want to compute these. So I'm just going to write them in as placeholders, right? Call them, you know, u of -1, u of 2, or something like that. They're placeholders. And then when you've done the substitution, you revert back to your original variable because those are nicer to plug in. Absolutely, those sometimes happen, especially when you're dealing with things like arctangents, arcsines. When you're dealing with inverse trig functions, figuring out, like evaluating the bounds is often messy. and you have to carry these arctans around and stuff, and it's not worthwhile. So you're just like, okay, at the end of the day, let me just convert back to my original variable and we'll evaluate that, right? But it does save you a little bit of time, right? It saves you one step, is I guess the moral at the end of the day is it saves you the single step of having to turn back into the x's. If you're doing a definite or an indefinite integral, right? Obviously you have to turn back to the x's because the answer is supposed to be in terms of x. But yeah, the benefit of doing the definite integral and changing the bounds of integration is you don't actually have to return to the x's, right? So this is a really nice way of thinking about it. Yeah, that's the reason why we actually changed the bounds. Yeah, generally the bar is only used with definite integrals. Yeah, because with an indefinite, you're not plugging anything in, right? You're just finding antiderivatives. So you're not, like, the bar doesn't have to come in there, because we basically, if we were doing a definite integral, we would kind of ignore these bars and then we would be done, right? Like we wouldn't do the last step at all. So that's what it would look like if we did a definite integral or an indefinite, right? Okay. I feel like there was something I wanted to say here. Well, let's do a definite integral, and I can point out something that is absolutely maddening. But this is just the way we do things. So let's do another example. I'll do another fairly easy one, and then I'm going to start to get into harder stuff just to show you what you can do. Okay, and you have to be careful when you do substitutions as well. Okay, so when I write something like this down, when I write log, this should be log, because I just spent a whole bunch of time harping on us about that. So log t over t. When I write something like this, implicitly I'm saying, there isn't a domain included, but implicitly I'm saying, 0 is not a thing here, negative numbers aren't a thing here, whatever the case might be. But you do have to be careful about this, because you can run into a lot of trouble where you're trying to find antiderivatives of functions potentially on domains where they're not defined, and you can get really weird antiderivatives, right? And I'll show you examples of that at some point in the future. Okay, but let's say we wanted to evaluate this thing. So solution, again, we're going to, somebody tell me what the substitution is, like what function is going to be u, like do you see a function and its derivative? Yep, great. U is equal to log t. So the du is 1 over t dt. That's exactly, everything worked out really nicely here. Exactly. So du is 1 over t dt. Okay, we've got no bounds of integration that we need to flip. So when we do this now, we've got log t over t dt is just going to become u times du. And that one's pretty easy to integrate. 1/2 u squared plus c. And then we switch back, right? We plug the u back in. And maybe I'll write this as, where do I want to put the 2? Let's put it there. Why did I write 1/2? No, let's put it here, like that. Okay, so that's not too bad. Note though, this is nonsense. Right? This is total garbage. Because when you write down an integral, right, I should be able to write down the integral of u du. And you all know that the answer is 1/2 u squared. And that u is just a dummy variable. When you write something like this down, u is a dummy variable and it has no association with the t that we have written on the left-hand side, right? They're completely and totally unrelated. So when I write the equal sign between these two integrals, that equal sign is nonsense, right? That equal sign doesn't mean anything. As a function, the left-hand side is log t, the integral of log t over t. The right-hand side, as a function, is the integral of t dt, right? It doesn't matter what variable I use. I should be able to replace the u with the t and get the same answer, right? So as an equal sign, this is nonsense, but we accept this as an abuse of notation in order to facilitate this computation, right? But strictly speaking, this is complete and total nonsense because the thing under the integral sign is a dummy variable. It's not supposed to have a memory, right? It's not supposed to know that it's related to t in this way. So listen, this is never going to be a problem in real life. This is worth pointing out as mathematicians, as people doing like the hard version of this course. This is nonsense when you write it down, but it's okay. Everyone accepts that nonsense. And in fact, again, most of the world who have done integral calculus doesn't even recognize that this is nonsense, right? It's so ingrained. It's such an easy thing to do. Most people don't even recognize that this is BS, right? So like I said, it's not something you ever have to worry about, but you should know. Because again, just like as a function, right? If I write down the integral of u du, it has no memory. That should be the same thing as the integral of t dt, right? Or the integral of x dx. And if you do any of them, what do you get? You get 1/2 x squared plus c, right? That is not the same thing as right? These are different. There's no constant which makes these two functions the same, right? But at some point I've written down that these two things right? I should be able to it doesn't matter what variable I use. I can write whatever variable I want in here. A function is a function, right? A function doesn't care what variable you call it. So when I say that these two things are equal, that is strictly speaking nonsense, because you should be able to evaluate those two things separately without knowing any relationship that u has with t, and you'll get different answers, right? And the fact that there is this sort of memory being passed on in this equal sign is the sort of nonsensical thing. So that's just kind of something to keep in mind. The variable it's an independent variable, right? It's supposed to not have any memory or any knowledge of anything else. And yeah, other things too. This function is defined everywhere, right? There's no possible bad u values. This function does have bad values, right? No, you do that, and absolutely. So what implicitly you're saying is like, right? Because there's nothing wrong with writing u is equal to log t. You're absolutely allowed to say, I'm going to create a new variable u, which is dependent on t. But whatever variable you use under the integral sign needs to be, how about this? You remember when we would write this, and this just means evaluate the integral, right? So on the one hand, I've got this function. And on the other hand, I've got this function, right? And at some point, we're kind of saying that these are true, right? Because like I haven't input a variable here because you shouldn't need a variable, right? The integral of a function is the integral of a function. What you call its variable doesn't matter. The integral of f of x is not different than the integral of f of z, is not different than the integral of f of w, right? It doesn't matter what the variable is called. So that variable is supposed to be memoryless. That variable is supposed to have no influence over the function itself, but it does, right? When we write this thing down, it does have a memory, and that's illegal, right? That actually is not okay. You're not allowed to write that down. If you interpret these as simply, what is this thing? It is the set of antiderivatives of the function log t over t dt. And again, the t doesn't matter there. You could have called it anything. What is this thing? It is the collection of antiderivatives of the function f of x equals x. And the variable name doesn't matter, right? When we say, by definition, the indefinite integral does not carry any memory of its variable, right? And so these are different sets. These are different sets of antiderivatives. Like I said, the majority of the world doesn't care about this because it's a nice computational technique and it doesn't care. And again, even most people in real life think the variable does matter, right? People are like, oh, these are complex functions. These are real functions. These are functions of angular momentum, right? They somehow have in their brains that the variable that you use matters, but of course it doesn't. These are all just different representations of the same function. So it's some sort of like, pedantic math thing, but I mean, strictly speaking, this is an illegal operation, right? It's just like for us, strictly speaking, this is an illegal operation, right? We're not allowed to do that either, right? But we do it because who cares? Can we use the integral of log t d log t? I'm going to say no. This is physics stuff. We're not gonna, right? I mean, I totally get this, and I appreciate what this means, but I'm not super comfortable with using this to begin with, and like in the sense that I know rigorously what that means. I also know rigorously what this means. But to try and justify to any of you what this is already kind of like, we're in territory that I'm not comfortable giving to you rigorously yet because the math is so hard, right? Like, we do this because it's easy. And the physicists especially do this because it's, it kind of makes things in some sense a little bit easy. But think about what you're trying to say here. If we take the convention in our class that dt is telling us what variable we're integrating with respect to, we're saying that log t is the variable that we're integrating with respect to, right? And you can see that, yes, you might believe that to some extent, but to make this rigorous is going to be hard, right? So yeah, I would strongly suggest avoiding that for this class until you learn what a differential form is. And you probably won't learn what a differential form is until grad school. Yes, and I'd love to show you all one day. It's really hard. It's really, really hard. Even if you don't do it on manifolds, it's hard just to do in Rn, right? Like, you all need to learn multilinear algebra first. So linear algebra, right? I imagine it all. It's taught it in 257 at St. George. It is not taught in my 257. And the reason for that is when I made my 257, right? First of all, I've known a lot of people who had TA'd 257. I've known a lot of people who have taken 257, right? When you talk to anyone who came out of, and I've had lots of TAs who took 257 at St. George, and universally, nobody leaves 257 knowing what a differential form is. Okay, so it's taught, and they spend a lot of time teaching it, and nobody understands them. So the idea is that if you're teaching something, which in some cases, some very famous mathematicians have taken this course, and they don't understand what a differential form is by the end of 257, you shouldn't be teaching it in 257, right? So yeah, I've actually cut it from 257 at UTM. We don't do it there. I tell them what it is and basically how to define it, but we don't actually spend any time on it just because there's some students who want to know what it is. Universally, once my 257 students hit third and fourth year and actually learn what a differential form is, they're like, yes, 100%, we can see why you didn't do this, right? Because I tell them, I explain them what a differential form is very, very quickly in 257. And I spend like, it takes like 20 minutes for me just flying as fast as I can, not taking any questions. It takes me like 20 minutes to give them an outline of what a differential form is. But it's just so overwhelming, they don't really appreciate like how hard it is, right? And then they go and actually learn what a differential form is and get their butts kicked. And they say, no, that doesn't make sense, right? So yeah, do any of you even know multilinear algebra? Right? It's not linear algebra, multilinear algebra. Yeah, tensors and stuff. Because I will teach you multilinear algebra in 257. And it is universally the most hated section. Okay, in 257, in my 257, which believe it or not, they don't do this at St. George for some crazy reason, I will teach you what a second derivative is. Okay, right? Which is crazy because you all know what a second derivative of a real valued function is. But in my 257, it's not completely trivial in any way, shape, or form. I will teach you what a second derivative is. And those, go ask anyone who's in 257 currently, right? Like, for example, a bunch of them are on the Discord. Ask them about higher order derivatives and how much they enjoy the math there. And they hate it. And differential like forms is all that math, right? It's all that math. Like, I don't think it's hard. It's just, until you have the mathematical maturity to absorb it, it's just, you can't, right? You're not, most students aren't mature enough to see those definitions and understand what's actually going on. Okay, so here, Let's do this problem. What's the substitution? Actually, first of all, can any of you do this? I think if you look at this problem, it's probably not obvious what an antiderivative is, right? So what's the substitution? Does anyone know? Let's make it a little bit harder. This is one of my favorite examples of a substitution because, you know, eventually you get into this habit. The first two are easy, and then you get something like this and you're stuck. Interesting. Okay, but what happens? So let's try that out. So if we say let u be, this might work. There might be some way that we can do this. So du is going to be what? 1 over 2 root x plus 7 dx. Okay, now what? Right, Rui, I like yours. I like yours a bit more. So I think actually there is still a way that you can make this work, but it's actually going to be harder, right? So this is an okay substitution, but it's a little bit tough. So it turns out the right substitution here is actually x plus 7. And let me explain why. So when I look at this integral, I say the thing that's really killing me is the plus sign under the square root, right? Because square root does not behave nicely with plus signs, right? You can't like split it up. I can't write the square root of x plus 7 as the square root of x plus the square root of 7. If I could do that, life would be easy. What I would much rather have is I'd much rather have that plus sign somehow come out and have the, you know, it be like x minus 5 or something times root x. If I could have that happen, if I could have the addition or subtraction or whatever the case be outside the square root sign, then this becomes much easier to solve. And by virtue of using this substitution, u is equal to x plus 7, we can actually make that happen. So watch what happens. So first of all, du is just equal to dx, right? We haven't done anything crazy. We haven't done anything like that. Now, when I try and integrate, when I try and do the substitution, so leave some space beside this because I'm going to come back, right? Like leave some space here. So when I try and do the substitution now, right, obviously I'm going to get stuck because I'm going to get, now don't write this down. I'm doing it just for illustration, right? Your integrals shouldn't mix your x's and u's because as blasphemous as the previous thing was, this somehow is worse. So, okay, I've got a problem here is that I need to transform everything into u's and one of my x's remain. So what do I need to do? I need to go back to my original substitution and figure out how now to write x in terms of u, right? And exactly, x is equal to u minus 7, right? So I'm going to plug that in. And again, don't ever write this. Okay, I'm just doing this for pedagogical reasons. U minus 7 root u. And now we have something which we can actually integrate, right? Because let me expand this out. I now get u to the 3/2 minus 7u to the 1/2. Yeah, this actually isn't that hard anymore, right? So what is this? 2/5 u to the 5/2 minus, that's gonna be 3/2, so 14/3 u to the 3/2 plus c, right? And now I can plug my u back in. 2/5 x plus 7. 14/3 x plus 7, 3/2 plus c, like that. And you know, you can check it, right? If you differentiate this, you'll see the cool thing happens. This is maybe in some sense a little bit surprising because we integrate x root x plus 7 and we get like, there's no, again, when you look at the answer, you're like, why are there these 5/2 and 3/2 terms and why am I adding them? But you're going to get magic cancellation. If you differentiate the right-hand side and actually see what you get, there's going to be a whole bunch of magical cancellation that's going to happen in order to give you the result that you want. So, you know, give it a try, see that it actually works, right? But yeah, sometimes you can use substitution not just to make your life a little bit easier, right? To be like, oh man, I really don't like that this plus sign is here. Let's make the plus sign disappear through substitution, right? Like that's the idea. If you see something you don't like, make it go away by substituting it away. And so that's kind of a strategy you can keep in mind, right? If you see something you don't like, substitute it away. Just make it go away by calling it the whole thing something new. All right, let's do another one real quick, and then we can take a break. Now, in something like 135, 136, this example that I'm about to do is actually its own its own lecture. Like people spend an entire lecture learning how to do this one. I have confidence in your abilities that I don't need to spend 60 minutes teaching you how to do this. Okay. With substitution using u of x instead of ub blasphemous, I mean, in some sense, all you're doing is abusing notation further, Yvonne, right? Like what usually we do when we write u is equal to x plus 7, we're saying u here is a dependent variable, right? Just like when we write y is equal to x plus 7. When we write u of x equals x plus 7, now we're saying u instead of being a variable is a function name, right? But I totally do this myself where I conflate these two things. When I say u is a dependent variable, but in some sense, it's also a function of those things. This is, again, an abusive notation. It's in some sense like more blasphemous because, again, I'm conflating a dependent variable with the function that defines the dependent variable, right? But again, nobody in the world is going to be upset with you. Everybody knows what this means. The only issue that kind of comes in is that especially first-year students tend to forget that y equals f of x. You know, when we write this, there's a difference between the output variable and the function, right? Like when I give this to my 133 students, they're always like, oh, you know, y is always the output of the function. It's like, no, the output of the function doesn't have to have a name, right? A function is just a machine. It gives an input and produces an output. You don't have to name the output, right? A function just always does that. If you give the name and output, that's fine. Writing here y of x is kind of even more blasphemous, right? Because y is not a function. Y is the name that you gave to the output, but everyone knows what this means, right? Everyone is saying, I know that y as a variable depends functionally on the independent variable x, and because I'm being lazy and I don't want to introduce some sort of function f, let's just overload this notation, right? So it, like, in a sense, it's more blasphemous, but again, everybody knows what you mean when you write that. And I did do this, right? I actually did do this myself right here, right? So, you know, I'm as guilty of that sin as anyone else because it's just a pain to do otherwise. But it's okay. We allow a little bit of blasphemy in our lives. Okay, so does anyone see what to do here? Oh, okay, good. Interesting idea. So let's take u to be sine 5x. Okay, so du is 5, what is it? 5 sine to the 4x cosine x, right? Hopefully I did that right. Problem is it looks like we're going to need 9 sines, right? Like this is u, right? This is the u that was defined, but then we need another 4 u's in the du. I should write dx here. No, but in some sense, it does look like it's the right thing to do, right? Because totally, the 5 and the 4 are related. So it seems like if you differentiate the 5, you should get the 4, right? Okay, sure. U is equal to sine x. Okay, now what? So du is cos x dx. But we've got a lot of coses. So we need one, right? In this substitution, we need to keep 1 cosine x, but then I've got 3 left over. Sum to product trig rule, maybe, like depends on what exactly you mean by that rule, but I think you're probably in the right way. So like what rule do you want to use? And actually this isn't the right substitution, but we can take it to its conclusion. And hopefully maybe it'll even give you the idea of what to do. What do I do with the other three coses? So I got to save a cos. What do I do with the other three coses? All right, what I actually want to do, so this is close. I'm actually going to take, here, let me show you what to do even before I do the substitution. Okay. Interesting. So okay, yeah. So yeah, exactly. So here, yeah, there's a couple of really good ideas. Ruyi, yeah, I think you did butcher that identity. You've got a right idea, but in the case of what you're doing, it turns out you actually want both of the exponents to be the same. And the fact here that there's like this extra sign hanging out is actually going to ruin the identity you're using, but you do have the right idea. If it was sine to the 4, cosine to the 4, your identity would be correct, right? So this is kind of the tricky thing. With trig, you have to be a little bit careful. So what we're going to do, actually, maybe let me tell you what the substitution is first. So we're going to let u be cosine x. Is that true? Yeah. Okay, so let me show you why. Exactly, there you go. So sine squared, yeah. So what we're going to do is we need to keep one sign, right, in order to make the substitution work. So we need to keep one sine x term for the substitution. And the reason why we chose cos x is because the power of sine is even, or sorry, the power of sine is odd, right? Which means that once I keep once I take one of those sine x's out for the substitution, what's left over is even. So I'm going to do now the integral. Here, let me just rewrite this very suggestively. Cosine 4x dx. So now I'm going to get sine to the 4x, cosine 4x, and then let me put sine x dx here, right? All I've done here is I've kind of just put it to the side so that we remember I have to save that sign. This is my like rainy day fund. I have to keep it. Oh, it's not negative yet, right? It's going to be negative after I do the substitution, but right now there's no like minus sign here. I mean, if you wanted to, what you could do is you could make this a minus sign and then put a minus sign in there if you wanted to, but right now I haven't done the minus sign yet, right? And then what I'm going to say is, okay, I'm trying to make the substitution cos x, right? But I've got all these annoying signs, but luckily I know how sine and cosine are related, right? Let's use this identity, basically the Pythagorean identity, to rewrite sine to the 4 as 1 minus cos squared x squared. Like this. Okay, so now when I use my substitution, I'm going to get the integral 1 minus u squared squared, u to the power of 4. And now this is where my minus sign comes in, right? Times negative du. I'm going to pull out that minus sign. And now it's just algebra, right? So 1 minus u squared squared, u to the 4 du. Unfortunately, there isn't a nice substitution there. In the second, did I forget a dx? Where is it? I see dx's everywhere. So did I miss an obvious dx? Right, because I've got my dx here, 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 and then du in the square brackets. Oh, maybe like I can put it in the square brackets. Oh yeah, oh, there's too many dx's up here. There we go. Is that better? Yeah, okay, cool. Yeah, there were too many dx's, right? Okay, yeah, let me download that in a second because Wolf or Zoom is a pain. So I don't see an obvious substitution here. I'm just going to expand this. So it's going to be 1 minus 2u squared plus u to the 4, u to the 4 du. And that's going to be, so what? U to the 4 minus 2u to the 6 plus u to the 8. All right. And then negative 1/5 u to the 5 plus 2 is the numerator. 2/7 u to the 7th minus 1/9 u to the 9th plus c, right? Because it's indefinite integral. And then what did we do? U is cos, so negative 1/5 cosine 5x plus 2/7 cosine to the 7x minus 1/9 cosine to the 9 of x plus c. And there we go, we have it. Okay? So, and again, I recommend that you all try differentiating this at the end to see that it actually does work, that this isn't just some sort of black magic, and that the answer you get actually does make sense, right? That you can actually differentiate it, it all makes sense. Yeah, exactly. And in fact, if it had been sine to the 4, cosine to the 5, or basically anytime there's this parity difference between sine and cosine, that's 100% what it is, right? Like if one of them is even, the other one is odd, the substitution is the even one. This is why it has high school vibes, right? Is because, you know, when you see this presented in a textbook, it'll be like, suppose that you have an integral sine to the m, cosine to the n. If m and n are both even, you do this. If m and n are both odd, you do this. If one is even and one is odd, you do this. And it's just you memorize what trick you're supposed to use. But at the end of the day, it all comes down to just, do you understand, you know, transform one of the sine or cosine into the other one. It's true, you have to use a different trick when you when they're all the same, when all the numbers are the same. Like if it's sine to the 4, cosine to the 4. And then there are even more advanced tricks, like what happens if they're both odd, right? You have to kind of do something differently there. That actually requires the next step, like when we do integration by parts. But yeah, so this is the gist here of what we do. Now let me, yeah, what is this? What is this trick? JPEG. Okay. When m is odd, yeah. Right, exactly, right? Which is, again, one of these, this is, you know, look at the parity of the numbers and figure it out. But again, it's not worth memorizing all these things. I don't have them memorized. I figure them out on the fly, right? And again, I think one of the exercises I'm going to have you all do in your next homework, but there's so many fun exercises that I want to give. But anyway, one of them is the derivation of a reduction formula. So when you look at more complicated integration techniques, one of the things that you often do is you have these formulas which allow you to take your integral and rewrite them as simpler integrals, right? That's kind of what we're doing when we do substitution. But you might need to apply it multiple times in order to reduce it to finally something that you can integrate. And there are lots of really cool reduction formulas that we have for trigonometric integrals. And I think I might make you inductively derive one of these, but I'll give you like hints on as to how to do it. But there's some like cool things that we have that, again, you wouldn't worry about in real life because you just plug it into Wolfram Alpha. Okay, so are there any questions about this so far? Like that's substitution. I'm not going to spend much more time on it than that. Substitution is super useful. It's probably the single most useful integration technique. It's super important. You do need to know it, even if you're doing pure mathematics. That being said, the one we're going to do next, which is integration by parts, is actually more useful. Like, because the things you can do with it are way cooler. But yeah, if there are no questions there, we can take our 10-minute break. So it's about 10:04, 10:00, it's basically, yeah, 10:04. So let's take 10 minutes. We'll come back at 10:14. We'll talk about parts. Might even finish parts today. We'll see. It depends on how far we go. And then we might actually start improper integrals for next week. We'll see. We'll see. Either way, let's take 10. Yeah, let's come back. Let's say 10:15 because I spent enough time blabbing. So 10:15 by my watch, and we'll do integration by parts. All right. See you all then. Okay. All right, so integration by parts next up, and then we're basically done. The integration techniques. Let me just see. All right, okay, cool. So integration by parts. Okay, so for this one, substitution was some sort of reversion of the chain rule, and now we're going to do the product rule, is basically how that works. Now, there is a typical sort of notation. We tend to use U and V's for this as well when we do it, so I'm going to be consistent with that notation. And we're going to, again, just assume U and V are both differentiable. Okay, and so we know that if we differentiate UV, again, I'm kind of assuming that they're functions of X, but I'm not going to write that in. What do we get? So we get U prime V plus UV prime, right? So all I'm going to do is do a little bit of manipulation of this. V du, so U dV is what I want to keep. So UV prime is equal to, maybe let me write this as UV prime like that, minus, okay, so I kept that one, so U prime V, right? All right, that's not crazy. And now if I try to integrate both sides, oh, I unplugged my surface, there we go. Then I'm going to get, and now I am going to write in the x's. U of x, v prime of x, dx is equal to U of x, v of x, all differentiated. But we know that's basically just going to be uv, right? So this is going to be U of x, v of x, minus the integral, U prime of x. Maybe actually let me write this as v of x, U prime of x, dx. Okay? And again, you're like, this doesn't look particularly interesting. Like, what can we do with this? As a heuristic, actually, maybe I should write the following as well. So this is obviously for the indefinite integral. And you'll notice there is no plus c, like I haven't written a plus c in because there is still an integral on the right-hand side. So it's not until you get rid of all the integrals that you have to put the plus c. In terms of a definite integral, though, there's no sort of weird changing of the bounds this time. It just kind of carries through, right? So for definite integrals, we'll have the integral from a, b, U of x, v prime of x, dx is, and again, here we're going to use that vertical bar notation. Right? Very nice, just saves us a little bit of time. A, b, like so. Okay. Now, in terms of remembering this, because there's a lot of stuff going on here, what we often do, and we kind of did this in the previous thing as well, what we're going to do is we're going to write v prime of x dx. We're going to call that dv. Again, this is kind of like writing d log t, right? Which I said we really shouldn't do, but this is useful for the mnemonic to remember what goes where. And the integral then becomes u dv equals uv minus the integral of v du. Okay, and to this day, honestly, this is still how I remember it. Like when I need to remember how to do integration by parts, this is the mnemonic that I say in my head. The integral of u dv is uv minus the integral of v du, right? Okay. Now, again, strategically, so this is the mnemonic. How do you spell mnemonic again? Mnemonic. I hope I spelled that right. Okay. Anyway, this is in an English class. Okay, cool. So in practice, what do you do, right? What's your strategy? Now, if you go online, people will give you a bunch of other mnemonics, right? Some sort of like acronyms or something. And I honestly don't know what they are. It's something like, because you need to figure out what are you going to set, you're going to see a product of functions. What are you going to set to be u? What are you going to set to be dv? Okay, sure. Which is like log, what is it, Ty? Like, can you write out like what that mnemonic is? I hate the mnemonic and I'll explain why, but like, I appreciate that it exists. And for the record, I can always create a function that will break that mnemonic. So you need to choose u and dv, right? Then compute du and v and plug into the formula. Okay. Yeah. So I hate it. That's absolutely true. Inverse trigonometric exponential. Sure. And this is what you would set. What is this? What you set u to be? How's the mnemonic work? Anyone know? Because I'm going to show you the real way of doing this, like the math way, right? Because we don't need no memorization. We're going to math it. So, while somebody tells me how this mnemonic works, let me show you the important thing. So in practice, here's what you actually do. Okay, so again, I'm going to rewrite down the formula, but I'm going to exclude the uv portion. Okay, so I've got the integral of ux v prime of x dx, right? This basically transforms into the integral of v of x u prime of x, right? There's some other stuff going on. There's a minus sign. Again, there's this uv thing going on, whatever. That doesn't matter. The point is you start with the integral on the left-hand side, and the hope is that by applying integration by parts, you arrive at an integral on the right-hand side, which is easier, right? So you start here, and this is where you end. And the hope is that this integral is easier, right? Because this formula, you can still kind of see it at the top of the page. This formula has an integral on both the left and the right-hand side. The left-hand side is where you start. The right-hand side is where you end. So you'd better end off somewhere that's easier than what you started with, right? That's your goal. Now, look at the formulas at the bottom of the screen here. They are exactly the same, except what has happened is I've pushed the derivative from the v onto the u, right? So I took this derivative here, like that thing, and I just went boop and pushed it onto the u, right? So I took the derivative off of one function and put it onto the other. And maybe I should write this like, right? And then I put it onto the u. So that's all we're doing. Okay, integration by parts is taking a derivative from one function and putting it onto the other. And in my brain, I kind of think of both functions as being bags of derivatives. And I'm just taking a derivative out of one bag and I'm putting it into the other bag. That's all that I'm doing. Okay, so integration by parts transfers a derivative from one function to the other. Parts transfers a derivative from one function to the other. Okay, what this means is that you can just immediately figure out what, depending on what you set u to be and what you set dv to be, you can just immediately figure out what the resulting integral is going to be once you apply your integration by parts. So let me give you an example of this. Okay, we're going to do the classic example, the first example that everyone does. Okay, and we'll start with an indefinite integral. I mean, it's all the same, right? So determine the integral of x e to the x dx. Now, the first thing you should always try is substitution, right? But again, there's no obvious substitution here. If it was e to the x squared, different story. Substitution would definitely work there. But let's determine this. So what I need to do is maybe kind of let me spell this out, but I would normally just do this in my head, right? And if you get good at it, you can. So what I've got here is I've got my function x. Oops, sorry. I've got x and I've got e to the x, okay? And I have to choose to differentiate one of them and then anti-differentiate the other, right? So okay, so what if I differentiate the first of these functions? What do I get? So I get 1, and then I'm going to integrate the other one, and I get e to the x. If I differentiate the second, right, and implicitly here, maybe let me write it out. Integrate the second, integrate the first. If I do this, again, you're not even worried about constants. Who cares that it's 1/2 x squared? You don't care about constants. And e to the x, right? So I can see that after integration by parts, if I do the first thing, that will be my integral. If I do the second thing, this will be my integral. Okay, where you just multiply them together. And if I look at this, I'm saying I definitely want to do the first thing. I don't want to do the second thing, right? Like the integral of e to the x is way better than the integral of x squared e to the x. Like we started with x e to the x. If I end with x squared e to the x, I've made things worse. I haven't made things better. I've definitely made things worse, right? So that tells me, and again, I normally just do this in my head, that I want to do the first thing. So what this does is it says you want to set u equals x and dv is e to the x dx, right? The thing that you differentiate is the u, right? Because it's going to become du. The thing that you integrate is going to be dv. In the second case, you would set u to be x squared and, you would be let u be e to the x and dv is x dx. Okay, so again, in fact, we'll do it both ways so you can see that this works out. But this really suggests to you that the way that's going to work is probably the first thing, right? So the first thing is what we're going to do. So I'll do the first thing first, and then I'll show you if we did the second thing, what you would get. So let's say and again, don't write down this table, just do it in your head, right? So let u be x and dv be e to the x dx. So that means that du is dx and v is e to the x. So IBP, and again, you can write IBP if you want, because nobody wants to write down integration by parts. So we get, and again, every single time I do integration by parts, I do uv minus integral v du. So uv minus the integral of v du. Right? And like I promised you, right? There's that integral, right? I could just eyeball it. They knew what it was. And once you get rid of your last integral sign, don't forget to put the plus c in there, right? And you're done. I mean, again, if you want to do a little bit more work, maybe you want to factor some stuff out, you can do that, but who cares, right? And that's how you do it. Now, you could do it the other way. There's nothing saying you can't do it the other way. You don't get a wrong answer. You just don't get an answer that you can solve, right? So if we did it the other way, right, what would we get? So let's set u to be e to the x. dv is x dx. du is therefore e to the x dx. V is, like here, you do have to worry about the constant, but again, that heuristic above is just to give you the rough idea of what the integral will be. So integration by parts gives you still, right, in my brain, uv, so I'm going to get 1/2 x squared e to the x minus the integral of v du. right? And again, just like I promised you, that's the integral that you get, right? So when you get used to this idea of pushing the derivative off one function and onto the other, you can just see what the correct integral is, right? Like you just know what to do. There's some examples where you need to use IBP again in the integral part of the first IB. Yes, absolutely. And or you might need to use substitution or some other integration technique, right? Especially when you have multiple integration techniques, it's relatively simple to create examples where you have to use all of them. But yeah, absolutely, you might need to do integration by parts again. In fact, if you're given this thing, right, you need n integration by parts to do this, because every time you integrate by parts, you basically just reduce the exponent by 1. So if you had like x to the 5 e to the x, you'd reduce it to x to the 4 e to the x, then x cubed, and then x squared, and then x, and then eventually you get it down to just e to the x. So in that case, yeah, you have to use n integration by parts. There are some more interesting examples. We'll do one in a second. But yeah, that's the gist of it. Okay, so everyone, like, I don't like these mnemonics. I don't think that they're useful because, first of all mnemonics are eventually wrong, right? Again, it's relatively straightforward to construct examples where this liate whatever mnemonic doesn't work. And instead, if you just like, oh, okay, if all I'm doing is transferring a derivative from one function to another, I can just look ahead and see what the integral is going to be. And does that integral look like something I want to do or not? Yes or no, right? And then you can figure it out from there. Yeah, so I think this is generally going to save you some work. And in fact, if you go and you take higher level analysis, now I don't think you would learn this in third year analysis, but you might see this in fourth year analysis. You definitely see it in grad school. This thing, this like thing that I've written here at the top of the screen where the start and end, this is actually the definition of the derivative for weird functions. So there are some functions, they're not really functions anymore, but there are some functions that only make sense under an integral sign. Okay. And in fact, some of you might be familiar with them if you've done any physics in the past. Has anyone here heard of like the Dirac delta function? Does anyone know of this function? Right? Okay. So there's the Dirac delta. Right. So just kind of as an aside, right? And the definition of the Dirac delta, for those of you, yeah, so the definition is usually, and you don't actually need it to be negative infinity to infinity, you just need it to be true on some interval containing 0. Okay, so the definition of this function that's called delta is that when you integrate f of x delta x, you get f of 0, right? Now the physicists will write down all sorts of just total nonsense about delta x, right? If you ask a physicist what delta x is 0 everywhere, but it's infinity at 0. And you're like, that's nonsense. That doesn't make any sense, right? Your function can't take on the value infinity, and it's defined, it's 0 everywhere on a measure 0 set. So it's, its integral should be 0. Nonetheless, there is a function that you can do, and it's defined like this mathematically. But now the question is, well, how do I differentiate delta of x, right? And the way that you actually do it is you say the definition. Again, let's just do negative infinity to infinity. Okay, so the function delta prime of x acts by doing this. Right? It is the negative integral of f prime of x delta x. Where does this formula come from? It is exactly integration by parts. Right? This is what did I do? I transferred the derivative from the delta onto the f. What did it cost me? It cost me a minus sign, right? Because the integration by parts has that minus sign in it. Yeah, I dropped the f of x delta of x part because you just say like, that doesn't make any sense. We can only evaluate the delta of x under the integration sign. This is the definition of delta prime, okay? So integration by parts has at the heart of it is how we actually differentiate some of these more complicated, these are actually called distributions. These distributions that only make sense under an integral sign, integration by parts is actually the answer to how we differentiate them, right? And yes, it does have a good physical meaning. It's like a point impulse, right? So delta of x does have a well-defined notion to it. It is mathematically rigorous. There is a mathematically rigorous definition of it. And there is a sense in which the infinity at 0 makes sense as well, because you can think of delta as being this limit of this like rectangular function as the widths get very small and the heights get very, very large. So there's a sense in which that makes sense, but not really. But this can lead you down, you know, if you take the physicist's viewpoint of this, it can lead you down into lots of weird things. Yeah, and it should show up in science a lot in general, right? That like point impulse notion is fine. But again, when you start working with these things, you're not working with functions anymore. And a lot of the sciences use these things without really understanding what they are. And precisely this is, you know, some of you might see a physicist write this down one day. E to the 2 pi I x dx is equal to 1, right? And this is just complete and total nonsense. So I don't necessarily expect any of you to see why this is true right now, but if you plot e to the 2 pi I x, it just goes around in a circle, right? It just traces out the unit circle is all it does. It's nothing crazy. So how, if you integrate in a circle from, you know, in negative infinity to infinity, you get the number 1. Right? Like, how is that possible? This is complete and total nonsense, except it's not. There's a mathematically rigorous sense in which this is true, but there's no way that any of you are in a position to understand it because we are not dealing with functions. When we write this down, these are not functions, okay? And I might need to put a minus sign there. The E there is not a function. The one there is not a number, okay? It is a Fourier transform. So the physicists write this down without actually understanding what it means. And like, if you compute this, it doesn't make any sense. You definitely don't get 1. So what is going on here, right? It's a little bit tricky. So we have to be careful about what we're allowed to do and what the physicists do and what the physicists get away with. You know, we just have to keep in mind that there's a lot of, again, throwing things at the wall and kind of hoping that they work. There's a mathematical definition of these things. Most physicists don't know them. Okay, so just kind of be careful of that. Okay. And yeah, because it turns out you need them when you solve really complicated partial differential equations. So you like enter a different space, you know, you're working in a distribution space instead of a function space, yada, yada, yada. Okay, let's do a hard one. This is one of my favorites. I love this one. I love this, this problem. You always get a student who comes to you and asks you how to do it. So I'm going to do it for you right now. There you go. Cosine of log x. This is not multiplication. This is function composition, right? Does this function show up in real life? Probably not. Can't imagine an example of this happening in real life. I guess it kind of does, right? If you took like e to the log, and we know that e and cosine are related. Yeah, so exactly, that's where we're going to end up starting. We're actually not in a position where we can use integration by parts yet. And let's kind of think about this. Basically, that log being inside the cosine is a real pain, right? Like, I have no idea how to do it. So just like the x root x plus 3 example or whatever it was that we did, what I want to do is I want to get rid of that log x in the cosine. So let's get rid of it. Let's substitute it away. Okay, so the first thing that we're going to do is let u be log x. So du is 1 over x dx. Okay, leave some space, right? Make sure there's some space here. So now let's do the transformation. So substitution. So we're going to get cosine. So log x is u. Okay, now here's a problem. I don't have a 1 over x dx here, right? So what do? Because I don't have 1 over x. Anyone? Any ideas? Log something equals 1 over x. Multiply. Okay, yeah, let's multiply by x. Let's try this. So, yeah, we're close. Log. So remember, it's the derivative of log, Sophia, that gives you something with 1 over x. And that is important to remember because that comes up a lot of times in like real math. But yeah, here's what we're going to do. So we don't know. Here, I'm going to write this in yellow because I'm going to delete it later. Okay, so we don't know what to do with this d of x, right? So let's come back up here. What is d of x? So dx is equal to x du, right? Kind of blasphemous because I'm mixing x's and u. What is x though, in terms of u? Like what if at this point, I took my substitution and I plugged that in? What is x? Is it u prime? No, u prime is 1 over x, right? But look at this equation. If you were to solve this equation for x, what would you get? You get e to the u. Yeah, exactly. And I'm just going to rewrite that like this. Okay, and voila, what I've done is I've taken this nasty thing, this cosine log x, which looked like a bit of a nightmare, and I've now transformed it into something that looks like maybe I could use integration by parts on it, right? Because it's now a product of two functions. And actually, you know what? Sorry, I'm gonna, because we're gonna use u's later. Let me change all the u's to y's. Sorry. And we're gonna use y because I can easily transform that. So hopefully your u's look close enough to y's that you can do that without too much trouble. There you go. So now we're using y substitution instead of, and again, you'll see why, because I want to use u and dv again, and if things are in terms of u, we could be in trouble, right? So I just want to write the substitution in terms of y instead. So now let's integrate by parts. And it turns out, in this case, it actually doesn't matter what, like e to the y and cos y are both these infinite sources of derivatives, right? You can just throw as many derivatives onto the exponential as you like, and it doesn't matter. And you can take as many away from e to the y as you like, and it doesn't matter, right? The exponential is not affected in any way, shape, or form. If you differentiate cosine, you get negative sign. If you integrate cosine, you get positive sign. So it doesn't matter which of these functions we differentiate, which of them we integrate, we're basically going to get the same integral on the other side as well, right? Up to maybe a minus sign. So it doesn't matter. Now, so let's let u be, I don't know, let's take u to be cosine y. It doesn't matter. Negative sine y dy. I'm going to take dv to be e to the y. dy v is equal to e to the y. Okay, and integration by parts gives e to the y cosine y dy. All right, uv, oh, that should be a y, is e to the y cosine y minus the integral of v du, but there's an extra minus sign in there, so it's actually going to be a plus e to the y sine y. Right? And you're like, okay, I don't think I've actually made my life that much easier, because I started with e to the y cosine y and I got e to the y sine y. Yeah, that's not a big improvement, right? I just kind of swapped out the cosine for the sine. Turns out though, the trick is to do it one more time. Okay, so let's let u be sine y. Du is cosine y dy. And you'll see why. This is a really dirty trick. Okay, so if I do it one more time, what do I get? So I get e to the y cosine y. Okay, that's just preserved from the previous thing. I'm not doing anything there. So let me put this into square brackets to indicate that this is where I'm doing the next integration by parts. So I get uv minus the integral of v du. So minus the integral of e to the y cos y dy. Right? And maybe let me write this on this side again, just so that we can see what happens. All right. And now you might be frustrated because you're like, okay, well, I could just do this forever. Like the integral e to the y cosine y is just where we started, right? So if we just keep integrating by parts, I just keep on adding e to the y cos y, e to the y. Oh, sorry, this should be sine y. I just keep on adding e to the y cos y, e to the y sine y, and so on and so forth. We don't actually ever result in an integral that I can solve, except, no, it turns out we're actually done at this point. Because look, this is the integral we're trying to solve for. And it shows up on both sides of the equation. So why not just move the right-hand side integral to the left-hand side? So we get 2 times the integral of e to the y cosine y dy is equal to e to the y cosine y plus e to the y sine y. And now I've moved the integral, so I do need to put a plus c here. Right? And now I just divide by 2. Let's maybe factor out the e to the y cosine y plus sine y. And you might say like, oh, that should be c over 2. No, because it's allowed to be all constants, right? You don't care. Okay, and now my answer needs to be back in terms of the original function. And it was, what do we do? We said y was log x. So we get of cosine log x is e to the log x divided by 2 cosine log x plus sine log x plus c. And of course, e to the log x is just x. And we're done. Why was the first substitution? Right? Oh, shoot. Every time I put my palm down. Right? So y is right here. Nice, right? All sorts of tricks. We had to use a substitution in order to get like the e to the y, like that log x out of the cosine. And it cost us an e to the y, but that's okay. And then we had to integration by parts twice, but it gave us this sort of like infinite loop sort of thing. But that's okay as well, because I could then move that to the other side in order to be able to solve for the integral I wanted. And then, we end up back where we want. So yeah, this is one of my favorite integrals because it's just, it's definitely on the harder side, but it's real nice. Not really. I wouldn't like, this is something it's important for a 136 student to be good at. But it's not a key sort of my objective for you to be able to solve really hard integrals. No. Yeah, I don't know, plug it in. See if Wolfram Alpha can do it. But here's the thing, I can give like, the 136 students, this is a hard example for them, but this is not a long example for them. There are integrals you can do in 136 that definitely take, that use 4 or 5 different techniques, right? So we're stopping here. I'm teaching you substitution and parts. In 136, again, they learn partial fractions, trig substitution, trig integration, and that's typically where they stop. They don't learn Weierstrass or rationalization. But there are questions you can give those students that use all of those results, right? Like every single one of them. So yeah, you could definitely do problems in 136 that take 2 or 3 pages of work and end up being very long. In terms of like real life, if you go and you do any physics, there are some physics classes where you do need to do this sort of stuff. So I remember doing quantum theory, and even in like an advanced quantum theory class, I remember doing integral computations that took 5 or 6 pages, right? You just had to do so many of them. Yeah. And in fact, like, you know, there are integration bees, right? Just like spelling bees, there are integration bees where, you know, you get into teams, somebody goes to the front of the room, an integral pops up, and then people just try and solve that integral as fast as they possibly can. And you learn all sorts of like interesting tricks in order to be able to integrate really, really quickly. It's actually kind of fun. Like there is, you know, solving really complicated, really nasty integrals can actually be a really enjoyable thing when you learn the tricks. And then it's just solving a puzzle, right? It's like you can see it in front of you. You've got this bag of tools and bag of tricks that you know. You start applying them and see if you can simplify it into something else where you can apply a different trick. And it actually it really can be a lot of fun. It's not, like I said, it's not something we're going to worry about. It's largely a useless skill, but yeah. So make sure when it says, did you mean beer? And you make sure you say, no, I actually want B. But yeah, an integration B is definitely a thing. Yeah. And like I said, this can be fun. So if you're interested in doing it, it's easy to find any textbook, you know, find the 136 textbook. My textbook goes into this a fair bit. Like I give the advanced stuff, the stuff that like Stuart doesn't have, right? So there are a couple of advanced techniques. So again, very famously, like Weierstrass substitution is one of them. I might actually make you derive Weierstrass substitution as a problem. Actually, I think I was going to do that, and then I realized because I put it in the book, some of you could just look at what I did in the book, which would kind of make it less interesting. But if any of you get an opportunity to look at Weierstrass substitution, it's one of the coolest substitution techniques, and its derivation is so awesome because it uses something called stereographic projection. It's a super, 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 super cool integration technique. It's just black magic wizardry that it works. And yeah, it gives you the ability to solve some really hard integrals. There's also, if you want a really advanced one, there's one that, of course, Richard Feynman is famous for, which is differentiation under the integral sign. So this one requires a bit of multivariate calculus, but you can kind of get away with it. Like you don't actually need to, if you want to prove that it works, you need multivariate calculus, but if you just want to use it, it's not a big deal. So there's differentiation under the integral sign. You can look that up. It is a really, really tricky one. And in particular, if you ever get an opportunity to read Feynman's description of his mastery of that technique, it's a fun story. He talks about, for example, he had mastered this technique relatively young, and he would have like engineering students at wherever, you know, MIT or whatever the case might have been. They would come up to him and be like, hey, listen, we've got this integral. We don't know how to do it. You know, this was, again, you know, pre-computer. We've got this integral. We don't know how to do it. Feynman would take it, like go into a back room so that no one could see what he was doing, and then come back out with it solved. And it, you know, again, the great thing is that you can always check your answer because you differentiate it. And so he like gained this reputation for being a wizard at integration. And it's just because he had mastered integration or differentiation under the integral sign. And, but it's a hard technique. It's not in any way obvious. So the fact that he had figured that out is definitely a pretty cool thing. Feynman, again, if any of you if you've never had the chance to like see any of Feynman's talks or read any of his books, it's definitely worth doing. He's a, you know, phenomenal orator and yeah, great storyteller. All right, I don't think I want to start improper integrals here. We'll pick that up on Thursday. And that's kind of what we were planning to do for next week. But if we get a head start on it, it doesn't. Yeah. And I think he cracked safes for a bit. And then famously, he once went up to an artist and was like, hey, I want to learn how to like draw and paint. And the artist wanted to learn physics. So they traded each other, right? And decided like one of them was going to, like Feynman would teach the artist physics and the artist would teach Feynman how to draw. So Feynman actually became a very strong drawer later in his life. So yeah, you know, something to keep in mind. It's never too late to learn, right? Just always keep that growth mindset about you. All right, everyone. So we'll call it there today. you can use this as a jumping off point for a wild world of integration techniques. No problem, no problem. And yeah, I mean, like if you want to get good at this, the answer is just do a ton of these, right? If you want to get really good at substitution and integration by parts. That being said, most of the stuff that I'm going to ask you is a little bit more on the theory side of this, right? Okay. All right. Yeah, sure.
Sorry, so you gave us the definition for a to the x, and I just, maybe I'm confused. Like, why does it hold for real x?
Right, because, so a to the x, let's see. So a to the x is e to the x log a, right? Or okay, and both of these things are defined for all real numbers, right? So the exponential function, right? X is a map from R to 0 infinity. So you can definitely plug in any real number X into it. And log is also defined for all real numbers, right? So that's why, like, that's the definition of how to exponentiate, with the idea that we don't actually know that this is true for all real numbers. So we're going to define it to be true for all real numbers. Is basically kind of the thing that we've taken here. We know it's true for rationals. This equation is certainly true for rational numbers. And so now we're just going to define this to be true for real numbers as well. And that is the definition now of this. Yeah.
Thank you.
No problem.
Have a good day.
You too. All right, everyone. I will see you bright and early on Thursday. Have a good Wednesday, and I'll see you then.